for sharing my screen and running ThinLink at the same time. All right, so back to the intro to Pandas. So, as I said, Pandas is short for panel data analysis, originally developed for financial data, which were panel data. But now it's expanded into a package that rivals SciPy in the number and complexity of available functions. And it's good for handling anything up to about, or any data sets of a tabular nature up to about 3 gigs of data. Above 3 gigs, it gets a little bit iffy, but there are additional tools that you can use to help maintain the functionality. So the key feature of Pandas is that every cell of every table has a corresponding row and column index that you can use to select by. And you can select rows, columns, subsets of rows, subsets of columns, individual cells, whatever. You can easily add, remove, transform, compare, broadcast, and aggregate data within and across multiple data structures. The data structures can be a wide variety of data types, including date-time objects. And you can, there's a very long list of available input and output formats. And you can also, I'll show this briefly, but it will be shown a little bit more in the parallel section, that you can also do a little bit of easy multi-threading of functions with Numba. There's also a simple interface with the Seaborn plotting library, which we'll show later in the morning. Pandas by itself has somewhat limited support for parallelization, but you can remediate that with by including packages like Dask or Polars, and Dask will be covered a little bit later in this workshop. If what you have are more like images or ND arrays, then there's also an X-array package that provides similar functions for higher dimensional data structures. But that's outside of the scope of this workshop. We will start by covering the loading and running. So when you want to, on HPC2N, this is what you need to load in order to use Pandas at the command line or in whatever GUI you launch afterwards. So if you're using Python 3.11.3, you need the SciPy bundle 23.07. NumPy, SciPy, Pandas, they're all part of the SciPy bundle, and they have been since 2020. If you want to use Matplotlib as well, you need these 2 functions. And although you can do some plotting with Seaborn without having to load Matplotlib, and actually you can call plots off of Pandas structures without loading Matplotlib explicitly either. But it still uses Matplotlib under the hood, so you will need if Matplotlib is a separately loaded library, you will still need to load it along with this tk-enter backend. tk-enter is what is used to display the figures. Pandas requires Python 3.8 or newer. So if you're still using Python 2.7, you're out of luck. And that's true for all of the centers. There is no Pandas for Python 3.7 and below. On HPC2N, there are a long list of SciPy bundles from 2019 onward, but you really only want to be using these, and again, skip the Python 2.7. For LUNARC, it's fairly similar, slightly newer. We will be using Python 3.11.5 and SciPy bundle 2023.11 and Matplotlib. Now, again, this is if you're working at the command line. If you do what I usually do, and that's to work in a GUI like Spider or Jupyter, then you don't need to load anything. It's included with the GUI packages. So on the LUNARC HPC desktop, all versions of Jupyter and Spider load Pandas, NumPy, SciPy, Matplotlib, Seaborn, and most of the other Python packages automatically. You can also, if you import Anaconda 3, then you'll also get all of those packages. But if you don't use Anaconda, then you will need to, again, you'll need to load the SciPy bundle. And this is what we offer for SciPy bundles. So mostly you'll want to be using this selection. On UPPMAX, all you need to do is load Python 3.11.8, or I think there's also the I think actually for Pandas you might need the there's this Python _ml _ packages. And I'm not sure that I can open a second thin link window to demonstrate this, but what I could do, I think, is to I will launch a CPU terminal and see if I can't SSH into UPPMAX on the CPU terminal. So let's start with 2 hours. And yes, that's the correct project. That should be okay. I'll just bump that up.
Pandas is included with Python 3.11.8. You don't need to load the ML packages just for Pandas.
Yes,
But
in the
you
next
do
session,
for a Seaborn.
Seaborn, you need the ML, but
Yes.
that is shown in the next session.
Yeah, and that one,
So this is
if you're going to be doing any plotting whatsoever with Pandas data, then you will probably want Seaborn, at least after I show you what it does.
Weirdly, it allowed me to import Seaborn after only loading Python 3.11.8. I could import both Pandas and Seaborn.
Oh, really? Okay. Let's see.
That would mean that you have it loaded, or you have a local installation of Seaborn.
Yeah.
Yes.
I don't, so hey, I will check. But no, I don't have anything loaded. I haven't built anything with Seaborn.
Double check the okay. So then it is rackham.upmax.uu.se. Tell I'm not used to using this one. And I grab my password from my keyring. Copy. Well, if it'll take it. Let me see if I've still got the use of my keyboard. Nope, that's the problem. All right, then that's not going to work for right now. Unfortunately, while I'm using ThinLink and Zoom at the same time, I sometimes lose the use of my keyboard, because there's not enough power to run everything at the same time. Anyway, so, but yes, you can take it on faith that Brigitte, you can trust that Brigitte knows the or what Brigitte said, which is that you can load Python 3.11.8 and get pandas if you only need pandas. Or if you only need NumPy, pandas, and matplotlib. On Tetralith, you need a few long and ugly package names like this. You need the this easy build package. But after that, it's all the same settings as it was for after that, it's the same settings that you need for LUNARC, and then if you're going to run Jupyter Lab, you import Jupyter Lab 4.2.0. And okay, so moving on, if you're not sure whether or not your pandas, or if you're not sure whether or not pandas is right for your data, you can follow this little handy flow chart. And so basically, if you've got 1D or 2D data, it's almost certainly a yes. And if named or time-stamped indexes would help, well, suffice it to say, if you don't think they would, yes, I would. So what we'll be covering for the rest of this section, and for part of the next session after coffee, will be basic object classes, data types, and their most important attributes and methods in Pandas. How to input and output Pandas data, how to inspect, clean, and sort them for later operations, and some basic operations, statistical, binary, vectorized, math, string methods. We'll go into group by objects briefly, but not a whole lot. We'll show a little bit how to compare data, implement some complex or user-defined functions, and perform windowed operations. And if we have time, we'll touch on time series. I will go into memory data saving data types, because I know most of you will want that, and how to prep for ML, but I may skip time series in the interest of time. So, oh, sorry, my mouse is a little bit flaky. So the main object classes of Pandas are series and data frame. And there's also a separate object class called index for the row indexes and column labels, if applicable. So data that you load from file will mainly be loaded into either series or data frames, and the indexes are typically extracted later from the after you've initialized the series or data frame. So a series is the 1D version, and data frames are the 2D version of the data structure. So a series is a 1D array with customizable indexes for the rows. So this is stored as a column vector, and you can also assign it a name for later addition to a data frame as a column, but you don't have to. And the same actually goes for the indices. You don't technically need to assign them. They will be assigned for you. So the indices can be numbers, strings, date-time objects, tuples, anything that is hashable can be used as an index. The default, if you don't choose anything, is a zero-based integer index. And as I mentioned before, indexes are themselves a pandas data type with many subclasses. The data frame, again, is the 2D version. Every column, and this is an important concept to understand. Every column of a data frame is a series. If you extract a column, it's a series. All entries that are all entries in the data frame are accessible by row and column labels, or in the case of the rows, typically an index. Although you can sometimes have column indexes as well. Any function that works with a data frame will work with a series, unless the function specifically requires column arguments. So for the vast majority of this seminar, I'll be only showing examples with data frames, but just know that you can do almost all of what I'm showing with series. And in fact, I'll be doing series operations anytime and every time I extract an individual column. You can also safely reassign labels and row indices as needed with a renaming function. For the rest of the talk, data frames will be abbreviated as DF. And if a series comes up, and I don't think it does actually, it'll be abbreviated as SER. There are literally hundreds of methods and attributes for series and data frames. I'll be covering many of the methods later in a lot more detail, but this is a very brief list of the important attributes. If you want to return the row, if you want to return the list of row labels, which you can treat almost like a series, you just call df.index, and that gets the row labels as an array of pandas data type index, which has a lot in common with series. df.columns returns a list of the column labels, also as an array of pandas data type index. If you need the list of data types by the column, you can just call df.dtypes. If you need the shape of the data frame, you can call df.shape. For a series, df.shape just reports the length. And also, if you need to convert back to NumPy for any reason, you can just call df.values. And that returns everything converted to a NumPy array, and that discards the row and column labels. You can also call .values off of .columns and .index to get a 1D array of the column and index labels. The data in a series in each column of a data frame is assigned a data type based on either built-in or NumPy data types or some other formatting cues. So the most important, whoa, what happened to that link? That should be a, okay. Anyway, so the most important data types are the following. Almost everything will be stored as either, if it's numeric, it'll usually be stored as either float64 or int64, but you can convert to 32, 16, and even 8-bit versions to save memory. All you have to do is just like as dtype or .as dtype. Then there's this object data type that stores most everything else except for datetime objects. The object data type stores strings, booleans, lists, tuples, and mixed data types. A lot of times, if you need to clean your data, your first sign will be finding a column designated as object type when you expected it to be some kind of numeric type. There's also many Pandas functions devoted to time series, so there are several data types date time, time delta, and period. And the first two are based on NumPy data types of the same name, and period is a time interval type specified by a starting date time and a recurrence rate. We won't have time to cover those in depth, but just so you know, those are there. And if you have date time type data, there's plenty of documentation to go through. There are also specialized data types for instance, saving on memory or performing windowed operations. And we will cover these a little bit more depth towards the end of the Pandas section of this course. So there's a categorical data type, which is a set-like data type for non-numeric data that has only a few unique values. And so the unique values are stored in the attribute .categories. And then for the rest, in the position of the data frame itself in memory, what it stores instead are very small, small integer codes that map to each of the categories, and they're stored in integers of the smallest data type that's needed to store all of them. There's also an interval data type where the indices are tuples of bin edges. And they all must be either open or closed on the same side, and they're usually output by, there are a couple of Pandas functions that are made for discretizing numerical data. And I will very briefly mention those towards the end. And there's also a sparse data type where it has this omitted value here that if it's been assigned, or once it's been assigned, if you've given it if you've specified so the omitted can be nan or 0 or any other missing value placeholder. The default is nan, but you can specify others. And so this placeholder value is stored in the data type, and where the data frame itself is in memory, all of the places that don't have data are compressed. So sparse is good if you have a table where the vast majority of the data are empty. But this is, again, far from an exhaustive list. I already mentioned index class objects. Well, stop scrolling. They've got to be immutable and hashable sequences to align the data for easy access. The categorical, interval, and time series data types all have corresponding index subclasses. Many of the methods and attributes of indices are similar to series, but index methods only exclusively return copies. For the same methods for data frames and series might return either copies or views into the original, depending on the method. And that actually has effects on how you assign the data, or what is allowed in terms of assigning the data. Just so you are aware, Pandas documentation uses a few different naming conventions for row and column labels or indices depending on the context. Usually indices refer to just the row labels, but sometimes they refer to both row and column labels if those labels are numeric. Columns might be used to refer to the labels and the contents collectively or only labels. Column labels and occasionally also row indices are sometimes called keys if they appear in functions that are designed to mimic SQL functions. And occasionally a column label is a name in the series, in the context of series labels. But I will try to mostly refer to indices as row labels as indices and column labels as column labels. So if you want to input or output data frames, there are a very long list of reader and writer functions. So the readers are the ones that that take in the data, and the writers are the ones that export the data to a file. And, oops, there's a typo there. This is not a complete list. This is only the most popular selection. 9 times out of 10, I would say you're probably going to only be using read CSV, because read CSV doesn't just read CSV files. It reads any text file that is where the columns are separated by some delimiter, even if that delimiter is just white space. The only exception to that would be if your text file is fixed width, and then you use this read fixed width file. There is no writer for a fixed width file, unfortunately. There's plenty of other formats. Another popular one you might use is read Excel. That one you would use for either Excel files or open document spreadsheets or ODS files. And you can write to them, and you can write to individual sheets within existing ones, or you can create a new spreadsheet and assign a particular sheet to the or assign your data to a particular sheet, which is really handy. And of course, there you can also read HDF files and even Apache Parquet files, and Python pickles, SQL queries, Google BigQuery, HTML, LaTeX, JSON. There's a whole bunch of them. Now, you do have to, I have to leave it to the reader to determine what quarks are needed, because there's probably 50 quarks for each of these, for each of those readers. For most of the text readers, like with NumPy's Gen from Text, you can also choose to load only some of the data. If you want to follow along with any of the examples, or do any of the examples in, say, like a Jupyter notebook or something, then what you would want to download is this exoplanets _5250 _Earth units.csv. I believe that's the same file that is being used in the that was used in the Matplotlib examples. So I'm reusing that because it's a very nice data set in general, and because I hope that with the Matplotlib exercises, you're already a little bit familiar with what's in the data, and that makes that will make interpreting some of these data cleaning functions that we cover in a few minutes easier. Well, so this is how you would read it in. Very simple. Index column equals 0 allows you to choose the first column as the index labels instead of assigning them the integer indices. And by default, the first column or the first row is assumed to be the column labels. And if you wanted to write this out to a different file, say a text file with a pipe separator and a comma in place of the decimals, like if you're, I know that's a popular format here in Sweden, but then you would use the .to CSV, and you would specify the separator here. In Gen from Text, in NumPy's Gen from Text, this would be called the delimiter, but in the Pandas functions, it's usually just sep, like for separator. And setting index equals true in this writer keeps the indices and assumes that they are part of the data. The default is to shed the index because, again, when you're first loading it in, if you don't tell it which column is the indices, it will just assign all of the rows an integer index, and that's not always very helpful. So you can just get rid of that when you write to a file. And if you do forget to set one of the columns as the list of row indices during import, you can do that later with this set index method. And then you just give it the column name that you want for the indices, and now that is the index. If you need to initialize it, well, stop. If you need to initialize a data frame or series from scratch, that's also fairly easy, much less common. But if you have lists or arrays, those can be converted directly to series and data frames, respectively. There is an index kwarg to assign a list of numbers, names, times, or other hashable keys to each row. And for data frames, you also have a columns kwarg to do the same for the columns. And you can also, there are also special functions for converting dictionaries and Python NumPy record arrays to data frame. So here's an example of creating a data frame from scratch. So there's a NumPy array right here in yellow. And then I've assigned a list of column names and a list of index labels. In this case, I chose them to be letters as well. That's perfectly fine. And then if you print it, it looks like this. And if you need to convert data frames or series back to NumPy data structures, you can do 2 NumPy, 2 dict, 2 records, and 2 string as needed. All right, cleaning and sorting. This is probably what you're going to be spending 90% of your time on whenever you're importing your data. At least in the parts that you have to manage with Pandas. There's a dot head function that prints the first 5 rows of data with the row and column labels. You can print a different number of rows or columns. Tail does the same thing. .info is one of the handier ones that prints the number of rows with their first and last index values, the titles, index numbers, and valid data counts, and the data types of all of the columns, and the estimated size of the data frame in memory. However, I will say you do not want to you don't want to rely on the memory estimate given by df.info. There's also a describe function that prints summary statistics. In unique is good because you can get the counts of unique values in each column. That can help you identify variables to convert to categorical. You can also get value counts to print unique value, and each unique value or sorry, stop moving. Sorry. For every combination of row and column values that you give it, it prints whatever values, all of the unique values. That's a lot more handy if you're only giving it just a couple of rows and columns at a time. You don't typically want to give the entire data frame to value counts, because then it just prints all of the data. There's also a sample function that randomly selects a given number of rows or a decimal fraction of the total number of rows. You can get n largest and n smallest for a particular column or set of columns. And now I want to go over this memory usage function, because this is going to be important for those of you who have data that is partly verbal. So the default is for memory usage to have deep equals false, and that just returns the estimated memory usage of each column at the location that the primary data frame is stored in memory. However, that's only accurate for numeric data. The sizes of strings and other non-numeric data are not measured with deep equals false, because what they're getting in what's stored at the location of the actual data frame is a pointer to the strings, because you can't trust that the strings are all going to be the same size in memory. So they have to be stored somewhere else, wherever they'll fit. If you set deep equals true, then instead of getting the memory sizes of the pointers, well, you still get the memory sizes of the pointers for non-numeric data, but it also adds the actual sizes of the strings and other non-numeric data from wherever they are, wherever else they're stored in memory that's not contiguous with DF. So I'll show an example with the exoplanets CSV file. So here I've loaded it in, just so you know what all the data types are like, and also why info is so handy. This is what you get if you use DF, called .info on your data. So lots of very useful information. So we've got 10 columns. A couple of them are object type when you're not expecting them to be, and I will show how to fix that later or momentarily. And so the memory usage that you get here is the sum of what you get if you call the actual memory usage function and leave deep equals false. And for comparison, I've printed deep equals true. So the top one is with deep equals false, and the bottom one is for deep equals true. Let's see if I can align this better a little bit. There. No. I hate this computer. All right, so the top one, you can see all the values are all the columns are the same size, even the index, even though the index, many of the index labels are strings. But for comparison here, down here with deep equals true, all of a sudden, most of these columns are like 8 times bigger in memory, or 7 or 8 times larger in memory. Because most of these columns are strings, except for these two, which have, when you first import them, they have white spaces in the, they have some white spaces that are confusing the data typer. But I'll get to that in a little bit. Here, this is a long summary table of all the different ways that you can select and assign your data. If all you can remember is just .lock and .ilock, that's usually enough. So for columns or any number of columns, you use dictionary syntax. You can also call the columns as attributes of the data frame. But usually what you see is this, or if you've got multiple columns, you just pass them as a list within the set of brackets. If you're selecting by row and column labels, and if the rows are non-numeric, then you use .lock, and you can use a dot, and you can just use a colon wherever you want all of the data associated with a particular row, or all of the data associated with a particular column. You can also select by numbers. So usually you just use .ilock with a row index, but you can also add a comma and select by column index. If you want to select all of the rows at a given column index, which is kind of rare, you just use this, you do it like this. .ilock : comma index. Here's one important thing I want you to note is that you can mix the use of .lock and .ilock. I mean, you can chain .lock and .ilock for data selection. That's okay, but you absolutely cannot do that for a data assignment, because you have no idea whether or not you're getting a view into the original data frame or a copy. And even Pandas can't tell you. Now, if you want to do conditional selection, most of the regular binary comparison operators will work and can be used inside of the brackets of df, df.lock, and df.ilock. The main restriction is that if you have more than one condition, each individual condition must be in parentheses. And if you have to combine conditions, you need bitwise logical operators, not the plain English versions. So down here, and also you cannot use the is operator within these. You have to use a dot is in, dot not in, or dot string dot contains to check for substrings or other things. As an example, here I've got I'm selecting the data selecting data just for pulsar planets, which were some of the first kinds discovered and still the smallest ever discovered. So here I've got dot lock, and then I've got two conditions, the pulsar planets, and again I've got all of the whole thing in parentheses. So df.index. We're looking for planets where the name, which is index, dot string dot contains pulsar or PSR. And we're looking for where the discovery year is prior to 2000. And that's all in one system. And then, so these indices here, those select from the rows. And then you just add a comma and planet type to get the column. And what it outputs is this. So there's the only system that was discovered like this is PSRB B1257 plus 12. But there are 3 planets in that system. Hooray! I believe that these planets featured prominently in a NASA Exoplanets House of Horrors article, which I highly recommend. So very soon we're going to have to take a break, but before that, I'm hoping we can get through get through most of the inspection and or the cleaning and sorting parts. So for when you're encountering bad data, if you need to find, remove, or replace missing or unwanted data, there's plenty of functions to do that. Pandas has its own functions for detecting missing data because it needs to detect not just regular knotted numbers, but it also needs to detect the date-time equivalent, which is not a time. And to do that, you need is in A. That's what detects the nans and nats. Or if you only want to select the valid data, you use dot not in A. Any of these functions down here will work on individual columns or any other subset of data frames, as well as the whole thing. Whoa, too far. If you want to remove entire rows or entire columns that contain bad data, there's this df.drop in A function. Many of these functions have an axis quard where you can specify 0 for the rows or 1 for the columns. And for the sake of space, I didn't include this, but it might be easier for you. You can specify axis equals and then in quotes, put rows or columns to be more sure of what you're selecting. And most of these also have an in place quard. If in place is false, what happens is that it returns a copy with the changes made. But if you set in place equals true, it returns none, and the data frame and the original data frame itself is modified. If you want to fill the nans with a specific value, you can use .fill in A. There's also a .interpolate function where you can use any of the methods that are available to SciPy.interpolate. If you find duplicates, you can remove duplicate rows or rows with the duplicate values of columns given to this subset quarg, and that makes it more aggressive. So generally, if you generally without arguments, drop duplicates only removes rows where the entire row is identical to a previously listed row. But if you give it a subset, it will only check if there are duplicate entries in a particular set of columns, and that's more aggressive. You can also mask by conditions, and you can also replace by value. This is what I'll use to fix our sample data frame in a minute. So dot replace takes a to replace value and then a new value here, and the possibilities here are very expansive. So I recommend you look at the docs for dot replace, because you can do all sorts of tricks with dictionaries and such to replace lots of different values at the same time. As we'll see in a moment, one thing that can catch people off guard is that Pandas assumes white spaces are intentional. So .isNA will not detect them. And that's because you can have numeric columns that have spaces in them, like for instance, Swedish zip codes have spaces in them for some reason. So if you have a column that is Swedish zip codes, then you're going to have a 3-digit number, a space, and a 2-digit number, and that becomes an index. But if you find that you have a data frame that has white spaces in a numeric column, and you don't want this, the fix for that is to select the column and set it equal to the column with dot replace, and then the space and comma nan, and then you use this dot as type to convert the whole column's data type. IsNA and not NA also do not notice infinities. For that, unfortunately, you have to convert to NumPy to get the indices of infinities. So anyway, here's me employing some of these functions on our sample data frame. So I'm loading it in, and just so everyone knows, each of these little function blocks has to be separately contained. So it's not like it is in Jupyter Notebook, where if you do this once in a Jupyter Notebook, it's set like this the rest of the time. In this website, they just have to be self-contained. Anyway, so I've imported the data frame, and I checked in the info or with the info method that mass and radius have white spaces in the columns, which are converting them to numeric. So I am assigning them to themselves dot replace white space with nan, and then converting them to float. And just for the heck of it, I also masked the eccentricity values where they're 0, because those are basically assumed values. And here I print, and now I print all of I print a sample of 3 rows and 3 columns, and this is what they look like now. And if I print info again, now our mass and radius columns are float 64. And I believe that now it's correct me if I'm wrong, we're supposed to take a break right now, or Björn or Brigitte?
I think break is nice. 15 minutes.
All right. I'm going to try and go a little bit faster for the rest of this, because I think we've mostly covered the fundamentals and the fundamental characteristics of the quality of the data. So I think And I'm going to try and go through the sorting and merging section a little bit fast because I think most of this is probably not something you'll use a whole lot. But anyway, just know that there are two options for sorting, and so a lot of operations, including all merging operations, require data frames to be sorted first, and there are two sorting functions to use. You can sort by the values of particular rows or columns, and or if the indices themselves are out of order, you can sort by the index with sort index. And as for merging operations, this is more or less the full list. There are 4 functions and 4 methods of the data frame. So there's concat, which kind of does what you think it would do. And then there's 3 merge options that are slightly different variations on the same thing, and that is to use SQL style joining operations. Then there's also these reindex like combine and combine first methods, and these essentially use one of the data frames as a template for the other, and then combines the two, except for the main combine function, and that merges 2 data frames column wise based on a given function. And then there's this join function, which is just a wrapper for merge. The different methods of merge and join are again SQL-like. So and the way that the logic works is kind of best demonstrated in this little image here. So if you have how equals enter, that's essentially the intersection of the 2 data frames. With how equals outer, you're getting everything aligned on where they overlap. And if you do a left or right join, depending on which data frame you select first, it either takes all of the first data frame, and for left, it takes all of the first data frame plus where it aligns with the second data frame, and it's the opposite for right. And when both row and column indices are passed to this on, that's sort of like the coordinates for alignment. If you have like if anyone is familiar with image registration, which is taking 2 overlapping images or taking 2 images with partial overlap and combining them where they do overlap, that's kind of what the on keyword kwarg is doing. You can also use reindex to add and sort indices, or add and sort indexes to add rows or columns if you want to. I'm going to skip this example because it's a bit long to explain. But hopefully, if you review this example on your own time, you hopefully can see the logic, because I've printed both data frames and what the product looks like. It's worth if you want to copy this to a Jupyter notebook, it's worth playing with the how kwarg to see how it changes. I spent an inordinate amount of time doing that and trying to figure out what was trying to figure out the patterns. It is kind of it usually doesn't work quite like you expect, so it's worth checking before you merge. So let's go ahead to group by objects. This is one of the most powerful tools in Pandas. The group by method lets you organize data hierarchically and run statistical analysis on different subsets of the data simultaneously. And that's basically, it sorts the data according to the values in 1 or more columns, collects them together, and then when you call any statistical function off of the group by object, which is the result, then it computes the statistics for each of those groups separately. The basic syntax is if you've got multiple columns, you can give it as a list. You can give a single column as well in this way, but you also still have to give it in list format. So if you're only giving a single column, you basically have to delete everything I've highlighted in yellow, but keep everything else. The other thing you can do is that if you've got a single column, you can say just by and then the name of that column. If you want to group by rows, you have to take the transpose of the data frame first. It only works by columns. Most data frame methods and attributes can also be called on group by objects. And again, aggregate methods will be evaluated for every group separately. That's what makes it super powerful. Group by objects also have an nth method, and that retrieves the nth row of every group. So you can get like just a little sample of every single group to check and make sure that your functions are doing what you think they're doing. N can also be a negative index. Groups in a group by object can be selected by the category name or accessed as an iterable with the groups attribute. However, I do not recommend trying to iterate over groups. It gets very slow and very complicated. And you can also broadcast separate functions to each group with a single command, given the right choice of method. And we'll cover that a little bit later in the operations section. So let's group our data frame, our sample data frame. Load it again, and now we're just going to print the df.groupBy and then print the first element of every single group. So we group by planet type. That gives us, and the planet types take the values of gas giant, super Earth, Neptune-like terrestrial, and unknown. And when you print the nth group of each, that means it's printing 5 different rows, 5 groups, 5 rows. And then, of course, you get all 10 columns of each of them because I didn't specify a specific one. You could also try on your own, you could try doing that by detection method as well, just to see, just get a little sample of the detection methods that are available. All right, operations. One of the things that that makes Pandas powerful is that many of the methods can be applied vector-wise. That means you don't have to iterate. You can just apply a function and it just goes straight through the entire row or the entire column, whichever is applicable to the method. So we saw something kind of like that already with the replace function. If that had been if the replace operation that we'd been doing had been on a column that we'd intended to stay as string or object type, then we could have just used .string.replace and added or subtracted or changed characters with that. Most built-in string methods can be applied column-wise to Pandas without any iteration. So you've got upper and lower, strip and rstrip, split and rsplit. Split is a little bit unique because you have this expand option and the in option, and that changes whether the outputs are lists or if they're expanded to multiple columns. For statistical functions, basically any statistical function that you're familiar with in NumPy, plus a few from SciPy, and plus a couple that are available in Pandas only, and that did not compile right. All of them are available as methods of data frames, columns, series, and any of these can also be applied group-wise to group by objects. The only trick is that if you're applying any of them to an entire data frame all at once, you have to set this numeric only equals true quar in each of these, because otherwise it'll raise an error because some of the values will be, or if some of the values are non-numeric, it'll raise an error. For data frames and group by objects, you also need to set whether you're aggregating along rows or columns. Well, you can aggregate along either rows or columns. The default is the default is just to aggregate over all of the data that you give it. So here's an example using a group by object. Have to redo the cleanup each time because these are each unique instances. But everything up to here you've seen before. The only new parts are these last two lines. So actually the only new part is the last line. So I group by planet type again, and then I'm calling the median off of the mass column of the group. So now you've got a median mass of each of these different planet types in Earth masses. So the gas giant, if you happen to know that Jupiter is about 318 Earth masses, you can tell that the average gas giant is a little bit more massive than Jupiter. And then you've got Neptune-like and terrestrial planets. Terrestrials are actually quite small. As for binary operations, the normal operators typically work on as long as both data structures that you're passing to it are the same shape, or if one is a scalar. However, there is a method if you want to apply, if you need to, say, multiply a data frame by a series, or vice versa. Or add or subtract or multiply. In any of these other operations, if you're combining, if one of the data structures is a data frame and the other is a series, you need a special method. If you don't have to use it, you shouldn't use these methods. So only use the df dot add, subtract, multiply, or divide df2 if you're combining data structures of two different dimensions. And they have to be compatible along at least one dimension. For everything else, the scalar equivalent is faster. There's also a reverse order version of all of these Panda methods. And that basically, like for instance, for divide, our div just takes the reciprocal of the original version. Comparative methods are kind of similar in that the normal binary comparative operators work just fine as long as you're comparing your series or data frame to a scalar. But if you want to compare any two data structures element-wise, and they have to be the same shape in this case, comparison methods are required. So the syntax is pretty much the same as these other binary operators, except the abbreviations are kind of like you would see in Fortran. So greater than is GT, less than is LT, and so on and so forth. And if you're doing any comparative expressions, scalar or element-wise, you can aggregate them by using .any or .all. Calling it once on a data frame aggregates along the column axis, and calling it twice collapses the entire value to the entire array to a single value for the entire data frame. You can also compare two data frames as long as they are identically indexed. They have to have identical row and column labels in the same order. Excuse me, let me drink some water. So just so you're aware and paying attention, this compare method is used in one of the exercises. So it's worth keeping the general location of this in mind. We're in the operations section. and the basic factorized functions. So if you have two identically indexed data frames or series, you can use df.1 compare, or df1.compare df2, and what that will do is that will print any of the rows or columns that are different. If it comes back empty, that means they're all identical, and you can go on with your day. However, it does not detect data type differences between visually identical data sets. For that, you would need to do this pd.testing.assert, assert frame equal, and then pass two data frames. Or assert series equal if you have two series, and then see if an assertion error is raised. All right, complex and user-defined functions. So what do you do if you have lots of different functions that you need to apply? Like, I don't know, median mode and multiply and all that stuff all at once. Well, ordinarily the best approach is to chain as many of the as often as possible, just chain existing vectorized functions. But if you can't do that because you have a really funky custom function, then there are 4 ways that you can apply that to your data, depending on the shape of your data and the shape of the return of your function. So there's map, there's ag, transform, and apply. The simplest is map. It takes a scalar function and broadcasts it element-wise to every element of the data structure. So function needs to be something that takes a scalar as an input and also outputs a scalar. You can't it can't take in and output arrays. And like I said, it's usually faster to apply vectorized functions instead. So here's an example. I've got like some temperature function that depends on the value of temperature. So really this is probably the most common application of map function, is where you have to vary the function depending on the value of the input. So I've got this function that looks kind of like a chemical rate equation. And so I've got this junk data frame that has a range of semi-realistic temperature values in around a protostellar disk, or in certain other chemical. Stop scrolling. So this is the original array here, and then applying this function. If I apply this map function, then we get this array back. So it's a one-to-one shape-wise function. Then there's ag, and what this does is this is sort of like the statistical functions, and that's what it does is that it takes all of the value. The function must take all of the values along a given axis and then output a single scalar. So statistical functions mostly work like this. And in this case, I'm just so map and map, ag, transform, and apply. They don't have to be strictly outputting numerical output. You can also use them to produce strings or other functions. So that this example takes an input and formats it as it takes a few values and outputs them as a string, like so. And this can be applied to group by objects. So ag, transform, and apply can also apply to group by objects. You just have to be a little bit careful with certain methods, especially with transform. So transform, what this does is it takes scalar or vector input and then outputs something that is also not a scalar. This can be very complicated because if you transform a data frame of X columns by a list of Y functions, and yes, you can apply lots of different functions at the same time with a dictionary syntax, but the result is something called a hierarchical data frame with X by Y columns. Sorry, this didn't render. I forgot I wasn't using Markdown. I'm not going to go into hierarchical data frames. You should avoid them whenever you can because they are very complicated to index and work with. And do not allow transform to modify your data structure in place. That is dangerous. Then if all else fails, you can use apply. It can handle aggregating, broadcasting, and expanding functions. And expanding functions are where you get a list-like output for each input. However, its flexibility and intuitive interface come at the cost of speed. But a lot of times you still might want to use it if your function varies by group, because transform is a bit weird. It receives group by objects in two parts. It takes the original column split into series and then the groups themselves as data frames. So you don't actually know what you're inputting until you get the erroneous output. But with apply, it's more like the way that it sees the groups is the way that you would expect, and it works like ag. So I've got an example here for how to use apply, and I've got an example for transform. I recommend that you go through these on your own and send questions by email or ask them later in the Q&A session as needed, because we are short on time and this is a long presentation. There's also windowing operations. So there are 4 methods for evaluating all of the functions that you've seen above by moving or expanding windows. There's the rolling method for standard rolling windows. You can also weight them by SciPy signal functions. There's the expanding window, which is essentially cumulative. And then there's an exponentially weighted moving window, which is kind of like rolling, except is kind of like expanding, except all of the previous data points are down weighted by an exponential decay function. For demonstration, whoops, did something get inserted? All right, something got inserted in a place that it wasn't supposed to be. All right, I apologize. Something got deleted in. Okay, there must be a malfunctioning block somewhere, so we'll just have to move on. It's here's something that's really important for later. If you have Numba installed, most of the previously discussed functions, except have an engine kwarg and an engine kwargs kwarg. If you set engine equals Numba and then engine kwargs equals, and then in curly braces parallel equals true, parallel : true, then what this does is that it sort of automatically parallelizes your statistics function or whatever other function that you've used column-wise. And this is essentially multi-threading. So this is not something that is this is not like MPI. This is just taking advantage of the fact that each core can sustain multiple threads. It's important to note that parallelization occurs column-wise, so the performance will only be boosted if the function is repeated many times over many columns. Many is being used a little bit loosely here. You get speed up even with just like 5 columns, but this is sort of a scientifically nonsensical example using the exoplanet's data frame, and with just 5 columns, you can get a factor of about 3 speed up. So here, I've decided that I'm going to take a rolling window, or I'm going to sample the array with replacement 250,000 times and take a rolling mean over 500 entries. So without the mean, or without NUMBA, this takes 24 milliseconds roughly. And with the with engine equals NUMBA and engine quarks parallel equals true, it only takes 9. So a factor of 3 speed up. You can also check your work with your data frames by just calling the plot wrapper off of your directly off of your data frames or other data structures. It's a relatively minimal interface, but you don't have to call matplotlib explicitly unless you need to do more advanced formatting. So you can use bar, histograms, box plots, area plots, KDE or density functions for kernel density estimations. It's kind of like a histogram that's smoothed by convolving it with a Gaussian kernel, so it looks much nicer and you don't get weird binning artifacts. There's pi for pi plots, scatter for data frames, and hexbin also for data frames. Most of the args and quarks that you can use to format axes can also be passed to any of these these .plot.kind functions, but I wouldn't recommend it because that can get really long and hard to read. So usually you'll still want to import matplotlib, but this is good for quick visualization. So let's say we take our usual exoplanets data frame and we want to look at the radius distribution of our planets. And just plotting a basic histogram with using roughly the cube root of the number of samples is the number of bins. It's a popular rule of thumb. And this is what we get. One line, whoops. One line, we get all this. And it automatically labels the y-axis for you in this case. So you can see it's a nice, interesting bimodal distribution. You've got your super Earths and giant planets separated. Whoa. All right, so just to try and, so we're in the advanced topics setting section, and I'm going to, in order to have at least a little bit of time with Seaborn, I'm going to skip straight to the efficient data type since I think that's probably the one that you're most interested in. Getting dummy variables, if you're interested in that, it's very simple. So just consult the documentation on that. So for categorical data, so if you look at the memory usage outputs of like a dummy variable array where all the categorical variables have been converted to numerical codes, you can usually get a factor of several memory savings in that, even if you are adding a number of extra columns. You can get the same benefit by converting to a categorical data type. And this, as we already mentioned, the way it works is that it's mapping all of the unique values of a given column to very short numerical codes that are that occupy the smallest amount of space required to render those codes. All you have to do to convert a column in an existing data frame is set the column itself, is to simply replace the column itself with itself.asType category. And if you're defining a new series that you want to be categorical, you just include dtype equals category in the quarks. You can get the methods and attributes of categorical data by with this cat accessor. So whatever you're calling whatever you're calling the method on, it has to have a .cat in front of it. So if you want to get the categories back, you have to call .cat.categories. You can use .categories alone, but only on categorical index objects, which are the indices of a categorical array. You can add, remove, rename, rearrange categories, and you can assert an order to your categories, which is nice when you, which is nice if you want to sort things in orders that are not, strictly speaking, alphanumeric. So it just so happens in this example that the names of the different planet types are just happen to be in roughly reverse alphabetical order. So if I wanted to call category, if I wanted to convert the planet type column to category, then I can assert that I can just get the category names, reorder them in reverse order, and then call set ordered equals true in this reorder categories method. And that will then assert that that gas giants are bigger than Neptune-like planets, which are bigger than super Earths, which are bigger than terrestrial planets. And unknown is, you can get rid of that. There are ways to get rid of categories. I just didn't bother in this example. But yeah, the memory usage, I've also printed the memory usage of each of those two columns. So converting the planet types column to categorical slashed the memory usage in by about half. What else here? You can also discretize numerical data, and that will also return categorical groups. And so this example, I recategorize the planets as slightly different cuts based on this plot. I'm not going to go through that example because we're low on time. There's also a sparse data type if most of your array is NaN or missing values. You can choose arbitrary fill values, and most of the existing NumPy universal functions will still work on sparse arrays. And again, mistypes up the link. And there's also these options. There's also these methods with the .sparse accessor. So density prints the fraction of data that are not NaN. You can get out the fill value. You can convert to a sparse data frame from a SciPy sparse matrix, and you can convert back to a SciPy coup type with this method. All right, in our last few minutes, I'm going to switch over to the Seaborn plotting library because